Howdy, everybody. Welcome to class number 2 in week 4. A potentially sunny and possible break from the rain for a little while today. So we've got a good glare on the whiteboard from the window over there. And I think it is going to eventually catch back up to us. But for right now, no blusteriness. So hopefully you're all safe out there. Hopefully you're enjoying your time. And we can do a little bit of physics right now, and that'll help take your mind off it. So for this week, PLC 4 for Friday, as usual. I think I put it up correctly in Canvas. I will double check that later on today, but I put it up yesterday. Hopefully it's ready to go. It's in the usual quiz format. Homework 2 is still for Tuesday so far, though I feel though we are a little bit behind on the stuff that I wanted to talk about. So I'll make an assessment on that, and possibly if we need to postpone that, I'll put up an announcement about it. When the homework is due, quiz will happen, so that's going to happen on the same day. And right now that's Tuesday of next week, so that's what we've got going. Almost done with grading the first quiz, so watch out for that. I'll be posting those back to you sometime this week. So without further ado, we're going to get on to a little bit more of interference. The situation we left off with last time was the double slit experiment, and we were looking at the intensities of the light. Now I tried to show you a nice pattern on the board of a two-slit interference pattern, and I don't think it really came through very well. So I'd encourage to go take a look and see what you can find with just searching for double slit experiment, and look for some images, and you'll see patterns of bright, dark, and sometimes you may see two patterns of brights and darks, and we'll be talking about both of those. But for right now, what we're talking about is the interference of the waves from the two slits. So I'm just going to go back and put a little bit more context into this, and give a little bit more background about what we're doing here. So this is double slit interference, and what we've got here is the basic setup is a screen opposite a thin piece of material with two slits in it. All right, we have a light source back here, which is emitting light towards the slits like that, and it simplifies the issue if we bring in a couple of conditions on the light that is coming in here. So number one, for example, we can see a better pattern if the light is monochromatic. In other words, a single wavelength of light coming in this way. That way we've only got one wavelength to deal with as we're looking at the analysis. All right. We're going to assume that these slits are very close together compared to the distance to the screen. I mentioned this a little bit last time. This is not to scale by any means. Typically, this is going to be in the tenths of a millimeter, possibly less, and the distance to the screen will be at least meter one, possibly a bit more. So you're talking about a difference of 10,000 in the factors between those two, and that's not going to be showing up in this drawing. So some of the things we are going to be assuming don't look like they should show up here, but in fact, when you do the experiment, they will. Now, the other last part to the light that is coming through from the left side here, it also really helps if it is somehow coherent. And what that means is that it's swimming together. It's all in phase, okay? Usual light is not coherent. Usual light has random phases. They are emitted with a phase this way, this way, this way. They're like different parts of their cycle is when they're leaving the bulbs. Let's assume that this light is different. This light is all at the exact same point in their cycles, such that they're going together like this. Now, The reason that's a nice thing to include is because we are effectively trying to analyze what is happening to the phase difference between the two waves emitted here in the slits as they hit the screen. We are trying to assess a phase difference. So it's nice to start them all with the same exact phase. And we can talk about how that happens maybe a little bit later, but for right now, let's just assume that we have coherent, which means same phase, and monochromatic light coming in from this side. So I'll just make a note of that here, and we can talk a little bit more about those conditions as time goes on. So coherent equals same phase. They all are at the same point in their cycles. All right, and monochromatic means same wavelength. Okay. All righty. So to this point, we've talked about the appearance of the central bright fringe due to the two waves, which have the same wavelength and have the same phase, and they're emitted, and they come to this point here by traveling the same distance. Now, if they have the same wavelength and they've traveled the same distance, that's basically the same idea as if I take two tires and they are the same radius and I roll them the same distance, will they go through the same number of revolutions? I think the answer would be yes. Now, if I took a tire that was this big and a tire that was this big and I rolled them through the same distance, well, now we're talking about two different points in the rotation where they're ending up. Okay. So if we talk about the two waves that are emitted, there we go. If we talk about the two waves that are emitted, and by the way, I do want to also point out this and one other thing. I am going to assume that through these slits, only a single wave is emitted from each one. So we're really only dealing with two waves hitting the screen here. This is the simple possible solution. So let's just assume that I've got one wave. Let's see, where's the middle here? Right about there? Okay, great. So let's just do one wave coming through here and one wave coming through here, hitting that same spot. Like so. And if I were really good, which I am obviously not, I would be able to draw the wavelengths appropriately and we would count them up. So I'm going to try it and then I'm probably going to erase all this and do another drawing. But okay, so let's suppose that we have like so, and I can do this. Like so. And notice that they both ended up with the same exact phase here at the very end. That's what we're looking for. Okay, so maybe I'm not as bad as I'm saying I am. I don't know how many I counted, but I tried to I have grids, so I can kind of cheat a little bit and make a wavelength grid. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So each one should have gone through 12 wavelengths. And their phase difference is 0 when they get to this point. This point here is directly opposite the middle of the two slits and is known as the central bright fringe or the central bright maximum. All right, this is the point where constructive interference happens due to the two waves traveling the exact same path. There is no difference in the number of wavelengths that they traveled to get from here to there. All right. So this is this is constructive, and it's the brightest one, constructive interference. Well, I should be careful. It's the brightest one as we see it. It's not the brightest one necessarily. They're all equally bright. Okay, they're all going to be equally bright. All right, so if we take another spot on the screen here and then we go, well, what happens if I go up here? Or likewise, I usually draw them up here, but likewise, you could go down here and it would be the same exact thing. You hopefully can see some symmetry about the center point here. If I draw a point up to here and I say, okay, how much further did the bottom wave go than the top wave? And then we need to assess that difference in the path taken, in the lengths of the path taken. We need to assess that difference. And then we need to assess how many wavelengths fit into that path length difference. Okay, this is what I was saying at the end of last class. So let's take a look here. If I do, say, this, and I say, all right, I'm going to now look at the path taken by the upper wave to this point here, like so, and I'm going to compare that path to the path taken by the lower wave, which is here, like so. Now, I can try to draw the waves again. I'm going to not do that because it's just going to get a little busy. I know, although I am very tempted to, I will not actually do it. I'm going to just say, suppose here that the waves get here, and I want to know what kind of interference we have. All right. So the question of what interference happens on the screen and what is the pattern I have to answer those two questions that I left off with in the last class. Number one was, what's the difference in the path lengths of the two waves here as they go up there? And then, how many wavelengths does that entail? All right, so question one is, what is the path length difference? And if you don't mind, I'm going to abbreviate that as PLD. What is the path length difference? PLD. And number two, how many wavelengths? In the PLD. How many wavelengths are there in the path length difference? Okay, so the path length difference, I told you that we are going to assume these slits are small enough such that only one wave is emitted by each one. So we're really only dealing with the interference of two waves. I'm also going to introduce you to the idea that I want to talk about the consequences of these slits being close together and that screen being far apart. And that is, you can't see it drawn like this because it's so shortened up and it's not to scale. But if I did take this distance and multiply by 10,000 and I put the screen that distance away, perhaps you'd think about the rays coming out of here and hitting this point on the screen as being almost parallel leaving because that screen is so far away, okay? So what I'm going to do is I'm going to assume that these rays are basically parallel when leaving. And that's going to get us around a bunch of problems. So in order to find the path length difference, I want to look at this triangle right here. Okay, that triangle right there. I know it's really small, as you see on the screen here, but that triangle is the key triangle. So what I'm going to do is say that the rays are away from the central maximum by some angle. So this is where that approximation of long distances of the screen comes in, and this is where the approximation of the small angles is going to come in. In other words, the angles of these two here that are leaving to hit the central maximum is basically horizontal, is basically 0 degrees. So what we're going to do is measure both angles of this ray and this wave and this wave to be the same angle. Doesn't look like that the way I've drawn it, but nonetheless, that's what we are assuming because of the scale of this drawing. It's just foreshortened too much. All right, so we're actually going to say that these angles here, like so, I'm going to actually go all the way over here and draw it there and say that angle there And this angle here, I'm going to draw it again all the way up to there and all the way up to there. It's the same angle. Now, like I said, it doesn't show up on my screen. I'm sorry, it doesn't show up on my drawing that way, but the reason is because I've got too small of a distance here for the screen, okay? Now, if those angles are the same, and I happen to know what the slit spacing is, in other words, if I take the middle of this slit and the middle of this slit, that distance right there to the middles, I'm going to call that distance D. All right, D will be my slit separation. Okay, and theta is the angle from horizontal. As the way we draw it, it's from horizontal. But I will say that this technically is not a horizontal angle because you could take the whole thing and rotate it around. Really, it's the angle from the central maximum. Okay, so with that, I'm going to redraw this triangle and make it a little bit bigger so we can see it. Just going to do that right down here. It looks like this. So this side being D here, and then I've got that going normally out to this one. So I'm going to have a piece here like that. And then I want the 90-degree angle to be right there. So that's there. So this here is the 90-degree angle. Now this is the chunk of the bottom ray, the bottom wave that's right here. Now, in order to find the difference in the two paths, what have I done? Well, so imagine that I've got two paths like this, okay? And I'm looking at, okay, what happens if I do this? Okay, so the question is, how much further has one of them gone than the other? Now, these are obviously constant length poles here. So what we have to think about is kind of like taking them like this and then going up like that, so that when I look at it and I say, this one's traveled a lot further, because if I take, I can't, sorry, I need another hand here. Can I get a volunteer? If I take the distance from here straight down, right, I can measure this distance, which is how much further the lower wave traveled, right? And that's this distance here, and it's that distance there, all right? Now, hopefully that's making sense. But so this triangle is this triangle, that's a 90-degree angle. And if you look at the geometry of the situation, the waves that came out parallel and went straight to the central maximum were at 0 degrees, and we went up by some angle theta. Well, that angle theta, therefore, must be this angle here. Because if these two things were directly parallel, then that angle would be 0, right? In other words, this leg of the triangle would be lying right on top of that leg of the triangle. And therefore, since we went up like this, the normal to this one went out with it, right? Like that. It went like that, and it swung it outwards. So however much I went up this way by, I went out that way by, and that's this angle here. So the PLD, right, the path length difference, is really this side right here. And if you look at a little bit of right triangle trigonometry, you'll notice that the hypotenuse is D, and if I take the opposite to this angle, that would be the side I'm looking for, and that's the sine. So really, the PLD is equal to D times sine of theta. All right, so this is the answer to question number 1. What is the PLD? Well, the PLD is d sine theta. All right. The second question is, and by the way, there's been no special assumptions here, okay, other than small angles, right? Other than small angles. So I will write that in here. We're assuming that theta is a small angle. Okay, so there's no assumptions other than that kind of large major one. But other than that, there's no assumptions at all, except for that one, which is the one that makes the whole thing go. Okay. I don't know anything about the interference that's happening up here yet. I've only answered question 1. I need to answer question 2, which is how many wavelengths are fitting into this distance right here. Okay, so suppose that I take this and I say, all right, look, that's a relatively small distance. If I compare it to the wavelength of the wave that I drew here, it's not going to be too far away from about a half a wavelength. So let's just assume it's about a half a wavelength. In other words, the wave here starts like this and goes there, right? And then it's going to come out and go out like this, right? It would come out and go like this. The wave up here is starting exactly the same way. It's going out like this and coming in like this. And so that's what I mean when I say they start at the exact same place in their cycle. That's what coherence is. All right, so they're both starting the same way. It's just that this one had to travel a little extra distance. Okay, so imagine I had 2 tires, exactly the same diameter, and I'm taking them and I'm rolling them. If I roll them the same distance, they go through the same number of revolutions. But if I roll one a little further, right, you're going to notice, right, if I got my 2 tires and I've marked arrows on the 2 tires such that they roll around, rolling around. Oh, I dropped it. Okay, I dropped my tire. Okay, they are still the same exact. They're still pointing the same orientation because the same tire has gone through the same distance. But now the lower wave went a little further, so now this tire is pointing this way and this one's going this way. So that tire's gone a little further. The question is, how much more of a revolution did it go? And this question is, how much more of a wavelength did it go? All right, let's suppose it went a half a wavelength more. That means now that what's matching up? You can't really see that part, so let me draw that in again. What's matching up? Okay, here's the top part. Here's the top wave. This is a total zoom in on these slits, by the way. I'm not really saying that very explicitly, but from the drawing here, it's like I'm taking this piece and I'm blowing it all up so you can see the triangle here, that red triangle, right, is this one? So the top wave is coming out starting with a peak. The bottom wave is coming out starting with a peak, but by the time it catches up to the upper wave, it's now in a trough, which means that I've got a peak added to a trough, and we did this yesterday with our visual math. Peak trough added to trough peak means destructive interference, right? These 2 waves are going to cancel each other out when they hit this part of the screen, okay? So suppose we've got destructive interference. That means the wave here, or whichever one it is, one of them has traveled an extra half a wavelength more than the other one. Okay, suppose destructive interference. So one wave traveled a half wavelength or some multiple of a half, like 1.5, 2.5, 3.5, right? Wavelengths more. Suppose destructive interference, this means one wave traveled half lambda further, or 1.5 lambda, or 2.5 lambda. In other words, it's like 1 plus a half, or not 1, it's like a number plus a half. So let's just call that m plus a half. If I just generalize half, 1.5, 2.5, 3.5, 4.5, it's like adding an integer to the half. So I'll just call m the kind of the index, and I'll say if m is 0, then that's the very first time that destructive interference happens. So the naming, the numbering is not quite on point, but so 0 is the first time destructive interference happens. M equals 1 is the second time destructive interference happens. I've gone up to another dark spot up here, right? 2 is the third time, et cetera, et cetera. Okay, so if we have destructive interference, then we know that d sine theta, which is this distance, must equal some integer plus a half of a wavelength. All right, so we're going to go here, and we're going to ask, okay, if it's destructive, then d times the sine of theta should equal m plus 1/2 times lambda. Let's see, is that showing up okay? Let me try to write that in a darker thing here. D sine theta equal m plus 1/2 lambda. Maybe a little bit easier to see that. Alrighty. So that's the situation with destructive interference. If I have constructive interference, what do you suppose is going to happen? Is the path length different? Or should I say, is the path length difference different? Okay, this is akin to asking the question, if I'm at a different point on the screen, but maybe I'm up a little further and I'm asking, okay, what if it's constructive interference up here? Is the path length difference still d sine theta? And I think you can see it is, because all we've done is we've increased the angle, but what that's done is it's widened out this triangle a little bit and made the path length difference bigger. Okay, so if I go up to almost twice the angle, I will have made this just about twice as big, and therefore it should be about 1 full wavelength. So this is 1 full wavelength now, and suppose that my path length difference looked like this, all the way out to here and all the way back to there. Okay, and now up at this angle, what's happening is that the next thing that comes out of here is that, and what's coming out of here is that, and now I'm comparing these two. These two waves are going up at a steep angle now, but it's peak lining up with peak instead of peak lining up with trough. This is constructive interference. Okay, if it's constructive interference, we still get the same d sine theta, but theta is different. Okay, but the expression is the same. That's what gives the expression the power, is that we can vary the angle, right? Now, notice what I've done here. If this is the path length difference, now I've got this thing here, and this is not quite the triangle I want, so I should really be a little bit more careful here. I really should be a bit more careful here. The triangle I want now has to be this one going up here, so that I get a right angle like that, and I get 1 full wavelength in here and starting again. There we go. All right, so without doing all of this baloney down here, all right, you get this idea. So the d sine theta is still the same side of the triangle, but now if I've fit 1 full wavelength in here, that means that if I have one wavelength, the path length difference is one full wavelength, and they're swimming in phase. And that means they're going to end up doing constructive interference because you're adding peaks to peaks, troughs to troughs. And remember that visual adding we did last time? Peaks to peaks, adding peaks to peaks gives you bigger peaks to peaks. That's a brighter fringe. That's a bright fringe at the M lambda. So if I have 1, 2, 3, 4, if it goes through some integer number of wavelengths, then I should be getting constructive. If it's an integer plus a half, that means it's gone just that little bit further, and now it's out of phase. And in fact, it's 180 degrees out of phase, right? Pi radians slash half wavelength. These all mean the same thing. All right, so these are the conditions for interference in the two slit setup here. Now, I mentioned that we were using small angles, and we are. So we can make one further approximation to this sign, and it's something that in the two-slit experiment I think will basically always be true. So this is a further use of the approximation. It's not a different approximation. It's the same small angle. But now I'm just going to say, okay, I'm going to take the sine of a small angle. What does that mean? Well, further use of small angle implies that the sine is approximately the same thing as the tangent of the angle, and that's the same thing as the angle. All right, so what I can do is write the sine as being approximately the tangent. Now, if I think about the tangent of the triangle, that's not really so helpful. But if I think about this triangle, the one where this wave line up here is the hypotenuse, this is the opposite side, and then this is the lower leg down here. If I think of this triangle, that's similar to this one. Or if you think this shaded in one, right? That's a similar triangle to this one. So if I call the distance from the central maximum up to here, I'm going to call that y because it's vertical. And I'm going to call the distance that the screen is from the slits, I'm going to call that capital D. That means that this tangent looks like y divided by d because d is that leg and y is this leg. So that's going to be approximately equal to y divided by d. And so we can rewrite this whole expression as little d times that thing equal to either this or this based on what type of constructive or destructive interference we have. All right, so the end usage of this, let me just write it up here as an addendum here. So this is going to be d times y divided by capital D. Same thing here, d divided by y times capital divided by capital, like so. Okay, now I just have to pick the appropriate y. The d value, the capital D value is not changing. Also, the little d value is not changing. We're not changing the slit separation. We're not changing the screen separation, at least not right now. But what we are doing is we're going up further to different points on the screen to find different interferences. So what this means is I have a bright spot here in the middle. I have a dark spot on the screen here. Further up, I have a bright spot. Further up, I have a dark spot. And the same thing is repeating down here. So this y will change based on where on the screen I am looking to see if it's constructive or destructive interference. This point was a destructive, so I could say this is like this is like destructive number 1. And if I went further up, if I went all the way up to up here, and I'd say this is, this is y of constructive number 1, or something like that, right? You can see that this y is much bigger than this y, and so these two y's are going to be different, okay? You have to choose the different points on the screen that coincide with what type of interference you're going to talk about, or what type that you think is happening there. Okay. So let's do this. Let's do, oh, I will say one other thing. Usually this angle, we don't know it. We have not been given it. What we are usually given are easily measurable quantities, like what's the screen to slit distance and what's the slit separation, right? And then you can look at the screen and you can measure how far these things are apart from each other, right? So normally the angle we don't know, and that's why this approximation, this one right here, comes in more useful because it's involving quantities that are more easily measured, and physics is ultimately we have to do experiments. So those are quantities you can more easily get your hands on. And when you do the lab on this, maybe later, might not be this week, might be next week, but when you do the lab on this, you'll see exactly what I'm talking about. All right, let's do a quick example here and throw a few numbers around to see if we can figure out something about some interference here. So let's see, do I have any numbers written down here? Ah, yes, good. Okay, so let's assume here, I'm gonna take this out now. I'm gonna redraw this. Let's assume that we've got this exact setup, okay? I'm gonna try and leave these conditions up so that we have them. And I'm gonna get rid of the rest of this down here. All right, so let's assume that we have the same setup as we did here for the double slit. That's a standard setup. Every time you see the words double slit or two slit experiment, that's the one we're talking about. All right, so let's suppose that we have this going on here where I've got my light coming in here. I've got the two slits like so. I've got a screen out here. I'm catching the light. Two slits, and they're separated by D. They always are. Like so. All right, so what we're looking at here is, let's suppose that I want to find the difference between a couple of different spots on the screen if I change the light source. Okay, so suppose I've got one particular wavelength coming through here, and I go, oh, look at the interference pattern, that's cool. And I mark out where the bright fringes are. And then I change the light source out, I put a different light source in, and now I'm going to look at the pattern on the screen, I'm going to mark out those fringes, and we say, oh, those are different positions of the fringes because the wavelength changed. And this probably will take you a little bit of time to come up to speed on, but it's all connected. And I will say this, mastering this type of interference is all about those two questions I erased up here, the path length difference and the number of wavelengths that fit into that. So if you can assess what's the path length difference and how many wavelengths fit in there, then you will be able to understand two slit interference, okay? And ultimately a lot of the stuff that comes past it. So altering the wavelength changes the two slit pattern, the interference pattern here, okay? Now the central bright fringe stays the same, but the outside fringes, the brights and dark patterns out here, are going to have a slightly different spacing if I use a different wavelength. So my question that I'm going to pose here in this example is, what is that difference in the spacing? All right. Suppose that I have a situation where I'm looking at a wavelength lambda 1, and then I swap it out to lambda 2. Okay? We know that the bright fringe is going to overlap here. What I'm going to do here is I'm going to draw on the screen the intensity pattern that we expect to see. All right, so the intensity pattern is going to be a little weird. It's going to be kind of on its side, but if there's no light hitting that part of the screen, then I'm going to dip down and touch the screen like it's a 0. And then if it's large, then I'm going to swing upwards, and we're going to see, oh, this is a bright spot. So the central bright fringe, okay, is going to look something like, say, this. All right, this is the central bright fringe. Or / central maximum. Okay, no matter which wavelength I shine through here, that does not change because the path length difference is 0 along that direction. Okay. Notice that it comes down and touches the screen. I'm expecting destructive interference at those 2 points. Okay. At which point, then I can go further up to a bigger angle and find the next bright fringe. So suppose that I go from here and I go up and then I go down again, like so. Okay? So this is going to be constructive peak number 1. This is where I'm expecting bright fringes to happen. Well, not here, but really here, right? Right there. That's going to be a bright fringe. Bright fringe. Okay? This is a dark fringe right here. I use the word spot and fringe. I'll try to stick with fringe because that's more of the standard terminology. That's a dark fringe. So really, I should be posting this over here like that. That's a bright fringe. I do not know how they came up with the word fringe to describe these things. But anyways, there you go. All right. Okay. So that's the situation with these. And what I'd like to do here. I know I told you to do this, but I'm going to go ahead and do it. Let's see here. Okay. Let me see if I can share my, I can't share my screen. Oh, can I? Oh, yes, I can. Okay. All right. Hopefully that's coming through. So this is what two-slit interference looks like. Thin, dark, I don't know, fringes, spots, those things, right? Interspersed with kind of more bright spots. Now, the middle of the bright spot is where the constructive interference is happening, but the rest of the bright spot, right, is all of this distance where it's kind of interfering constructively, but not all the way. It's not all the way constructive, not all the way constructive. Okay, now it's totally gone, destructive. So the mindset is, unless you have total destructive interference, there's a little bit of light there. And that's why the constructive fringes are wider than the destructive dark fringes, I guess. Okay. So what I'm drawing here is this that pattern as an intensity pattern on the board. I'm drawing a brighter intensity going to 0, and then a brighter intensity and going to 0. Okay, like so. All right, so hopefully that makes sense. I will also alert you to another piece of terminology that I use, and in case you are not a fan of the Muppets, you should be. And if you are, then the analogy of this is the Dr. Teeth diagram hopefully makes sense. This is Dr. Teeth. This is what the Dr. Teeth diagram is, right? That's what I say. Okay, so there you go. If you don't know who Dr. Teeth is, then I will leave you to do a Google or search on that later. I'm not going to do one right now because it's good stuff. All right, so bright, dark, bright, dark, bright, dark. All right, okay, so at this point here, another bright fringe. Okay, back to this example. What I want to do is I want to pick the third constructive fringe away from the central maximum. So here is the one in which there is 0 path length difference. This is the one in which there's 1 wavelength path length difference. So this is fringe number 1. Okay, so in the counting scheme of this right here, I've got m equal to 0 in the middle. I've got m equal to 1 here and here, because it's the same angle either up or down. And then I would go to m equals 2 and then m equals 3. All right, and so that's how the y component is also assessed. So I want to pick the third bright fringe. That is to say, the m equals 3 bright fringe. Now I'm going to shine these 2 wavelengths through, and I'm going to say what's the difference in position of those 2 third order bright fringes. What is the difference in y between the 2 spots I get from that wavelength and that one, right? What's the difference? Okay. All right, so there's my question. What difference occurs in the position? Now that position is measured from the central maximum, so this is the point right through here where y is equal to 0. All right, and then I measure up. This here would be y to number 1. And then I want to go to number 2, and then I want to go to number 3. And I want to measure that position. Then I want to swap the wavelength out, and then I want to go from 0 to 1 to 2 to 3. Again, they're going to be in different spots. How much of a difference is there? Okay, let's throw a few things around and see what we can figure out. All right, now is time for all of this to go. Okay, so let's take a look at the constructive interference situation, because that is the one that we are dealing with. So this is for construction. We know that d times sine theta, but remember I'm going to be in the small angle approximation, and I'm explicitly asking for the y value. So I'm going to use y, and I know I'm asking for number 3. And this is going to be equal to m lambda. And I'm just going to call that lambda 1. Now, m3, well, that's just 3. Like so. 3 lambda 1. All right. For the other case with lambda 2, I'm going to get the exact same thing, but the y3 is going to be a little bit different, and I want that difference. So what I'm going to do is, let's just go ahead and write this out again. And I'm going to write y3 as a slight difference here. Maybe I'm going to put y3, I'm going to put it as Y, what do I want to call it? Y31? Oh, I'll call that one 31 and that one 32 to go with the wavelength. How about that? So this is equal to, again, M3 times lambda 2, and that M3 is still 3. Okay. So what my goal here is to do is to find a difference in these two expressions. Okay, so I'm going to find a difference in these two expressions basically by just subtracting them. There are a couple of different things I could do, but the most brute force way is to just go ahead and subtract these two. So if I subtract these two, then I'm going to get this minus this, but little d and capital D are the same because I haven't changed the setup, only the y is different, so I get a difference in the y's on this side. I'm going to get d over d times y31 minus y32. And then on that side, the 3 is still the same because that's the fringe number. So I'm going to get 3 times lambda 1 minus lambda 2, like so. All right. Therefore, if I want this distance here, all I got to do is flip that over, multiply it on that side, and I can put some numbers in and see what happens. All right. So let's do that. I'm just going to call that the delta in y3 is this here. And so delta in y3 is capital D divided by little d times 3 times delta in lambda. If I do 1 minus 2. All right, so let's assume that I can throw a few numbers in here. What if I have a slit spacing? Let's do this. Okay, I'm going to evaluate this here. Nope. I'm going to evaluate this here at a slit spacing of, let's do 0.5 millimeter, 0.5 millimeters. Let's do capital D of 1 meter, and let's go lambda 1 of 600 nanometers, lambda 2 of 480 nanometers. Okay, all right. So as you can see, and this is typical, by the way, right? This is typical. We get the information in the units that is appropriate to the measurement. These units are appropriate to these measurements. The wavelengths are always going to be measured in nanometers, especially for visible light. The distance to the screen is a meters, it's a meter or more, it's measured in meters, so that's in meters. And then the slit spacing is typically tenths of a millimeter. So in this case, I just chose 0.5 millimeter, okay? So one of the things you have to do is get these all to be copacetic. Now, that being said, look at what the expression is telling us. I'm going to divide these two, which means these two units could go away, and whatever the units of this are can be whatever the units of that are. Or I could say little d, and these units go away. And then I'm going to get the units of delta y and whatever I have of these. So you can kind of pick and choose, but my suggestion would be make two of these the same and then realize that whatever you're calculating over here is going to be the same as whatever you got over here. Okay. In this case, what I think I'm going to do is, so I can pick either meters or nanometers. I guess I'm going to pick nanometers. I'd really like to pick millimeters, but I don't have that. I guess I kind of could do that. Change these all into millimeters. Nah, I'm just going to leave it in nanometers. That's the easiest thing to do. All right. So here what we're going to do is we're going to get 3 times 1 meter, and I'm going to divide by 1/2 millimeter. So that means I got to put the factor of 1,000 in the top. So now I got to change all that. Or no, I'll just leave it in the bottom. I'll put it 0.5 times 10 to the minus 3 here, meters, like so. And I'm going to multiply that by the difference in nanometers here, which is 600 minus 480. So therefore, my delta y is going to come out in nanometers. Okay, fine. No big deal. It's going to be a lot of them. There's going to be quite a lot of them. So what do we have here? Well, this is going to be 120 nanometers. This is 0.5 times 10 to the minus 3. So if I just shove the 10 to the minus 3 up top and then I hit 5, that's going to make 2. So that's become a 6. So this is 6,000 times 120. 6,000 times 120 would be 72,000, but it's got another 0 on it, so it's 720,000 nanometers. All right, so how big is that? Well, you know, a nanometer is 10 to the minus 9. So if I take off these 3, it's 10 to the minus 6. If I take off those 3, it's 10 to the minus 3, and that's in the millimeter range. So this works out okay. It's about 0.7 of a millimeter. It's 0.72 of a millimeter. Pretty close together. And by the way, those are, in terms of wavelengths, those are the kind of outermost visual wavelengths for our seeing. It's not, they are, I mean, it's a good rule of thumb, okay? Typically, you might be able to see a 650 or a 670, and that's in the red side, and then on the blue side, 480, that's kind of a green, I suppose. So in the blue side, you'd be lucky to see a 430, maybe a 440 or a 450, something around like that. So that'd be in the deep blue side. All right, so hopefully that was helpful, and we've gotten the positions of the fringes dealt with. So we're going to move on to the next type of interference here. We're going to, I want to just kind of give you a little look ahead here. We're going to come back to this, okay? We're going to come back to this because there is more analysis to do with this type of setup. But right now, I just want to concentrate on what happens with the interference of 2 waves. And then we'll deal with the extra piece that happens later, all right? So right now, this is all I want to get through, I think, out of this. And then we'll come back and we'll look at the patterns a little bit more in depth, probably next week. Okay. Okay, so let's go from there and let's do, oh, you know what? I want to do another thing before we leave this. I want to do one other thing, which is to talk about what's the maximum possible situation here. This is the other thing I want to talk about. Since light is coming in from the left and going through the slits, let's talk a little bit about why interference occurs. Well, I drew you that picture of the wavelengths, but in reality, that's just one direction, okay? Once the waves come through these slits, they spread out in all directions. And this is a situation that is observable in the ocean. If there's an ocean wave coming through and there's a big rock, you'll notice that the wave breaks off the rock and kind of in the water makes a big pattern of kind of a circle centered on the rock. And so that's what's basically happening here with these slits. So physically what's happening is the wave comes through here, but if I were to draw the crests of the waves, right, they would be kind of like this. And the same thing would be happening here. Right, there would be waves like this, and they would be spreading out in all directions, exactly as if you dropped a pebble into a pond and you watch the ripples going out like that, this is a half of one of those. So the rays that we were drawing in the first part are really just things that are going out perpendicular to these wave fronts, like this, right? They're going out like this. And this is what I mean when I'm talking about the wave spreads out in all directions. So I can pick rays and draw them and say I've got a wave overlapped on top of that. Okay, back to what I wanted to say, which was, let's talk about the maximum situation here. The maximum situation is the one in which interference happens at 90 degrees. Okay, that the angle that the waves make, the ray that we're interested in, is at 90 degrees from the central maximum point, right? So that is, in other words, going straight down or going straight up. All right. Past that 90 degree angle, we can't see anything because the part in which light is landing is all kind of in the front of this two-slit interference, two-slit screen here, right? The light's coming this way, and it comes through here, and it's going to land somewhere on the screen, but I can think of the screen as kind of wrapping all the way around up here and capturing the 90 degree interfering waves up there. So the one way to find the maximum possible number of fringes that you're going to see is to set the angle to 90 degrees. Okay, and that means when you look at this, at the expression of d sine theta equal to m lambda, so I want to know how many constructive bright fringes do I see, then what I'm going to do is set this equal to 90 degrees, and then say that the maximum m, this is going to be the maximum, is equal to lambda divided by d, right? Because sine, no, wrong way, d divided by lambda. The sine is 1, and so I have to swing that over here, and that becomes 1. So the maximum number of bright fringes would be the ratio of little d to lambda. Okay. So you can see that as the slit spacing gets smaller and smaller and smaller and smaller and smaller and smaller, eventually you only get 1. And that's the time when the slit spacing, the distance between the two slits, is the same as the wavelength. So if I have a situation where I have a wavelength of, say, 600 nanometers, but my slits are 600 nanometers apart, what do I get? I get one big fringe. I get one central bright fringe. This thing right here just expands all the way out and becomes really big. As the slits get closer and closer and closer together, these fringes get bigger and bigger and bigger and bigger. Kind of a fun situation. And that's why one of the reasons we know the ray model doesn't work, because when you try to squeeze light down into a smaller and smaller, force it through a smaller and smaller opening, it spreads out more and more and more. And it's one of these situations in physics that we run into again and again, and it's, I think, what is responsible for why physicists are so hard to deal with. It's because the phenomena that we try to explain is doing the opposite of what you want it to do. And so that's why physicists are so ornery, because we do the opposite of what, because we're just imitating nature, right? You want to say, hey, I want to get one ray of light, and so you're narrowing the light beam and narrowing and narrowing and narrowing and narrowing, and you're narrowing it, but as you're narrowing it to get it smaller and smaller, it's spreading out and doing the exact opposite of what you want. And that's just what happens. I guess I don't know how to tell you otherwise, but okay, so there's that. I want to also talk about some of the other interferences that we had going that I mentioned yesterday, which involved a wave through a material with an index compared to a wave that bypassed that material. And so that's one situation of wave interference. And I also want to hit the other one, which is reflection off a boundary between materials with indexes. So let's do those. And we'll come back to the double slit in a little while to reopen that can of worms and look at it in a more in-depth way. So this was just a taster. Keep this on your burner because this is going to come back later. Alrighty, let's take a look here. If I thought of a, what do I want to call this one? Kind of like refraction. This was number 1, I think I listed. This is the one in which there's a material with an index. Let's suppose that we have a material with an index n and it's sitting in air. What we're going to do is shine a beam through air past this object with index n, and then we're going to shine a beam right through the material with index n, and then we're going to have them interfere after they're both past the material, right? Maybe it's a block. I got a block of stuff here. I'm going to shine them both through, and then I'm going to have them interfere out here and say, what kind of interference am I expecting? All right, so suppose that I have a wave here going like this. Like so. It's not the most even wave in the entire history of whatever. What I'm going to do is have a block of stuff here. And this is the material with index n. Whereas this wave was propagating through air, or say vacuum, that's the same thing. What we're going to find, and I mentioned this in the last one, is that the wavelength inside there is reduced. So if I, again, with the same idea as last time, I begin with single wavelength coherent light. So in other words, the wave I'm about to draw here starts at exactly the same place in its wave and has the exact same wavelength in air. But in a material n, material with index n, we find that the speed is reduced. And that is ultimately what the definition of the index is. It's c divided by v, and that's what n is equal to. So if you think about how to find v, it's just c divided by n. All right, so this is how you start thinking about, okay, what's the speed of light in glass? Oh, it's c divided by 1.5. Okay, what's the speed of light in diamond? Oh, it's c divided by 2.5. Okay, so it's getting lower and lower, right? And that's how the index tells you that the material is such that the light travels slower through it, okay? Now, if you think back to the wave relationship that we talked about last time, remember that v was equal to lambda times f, right? The frequency multiplying the wavelength. So if I have a situation here where I can say, look, I have a wave that's traveling approximately at c, and it has a wavelength. And now I'm going to compare that to the situation here where I've got it inside the block and its speed is lower. Why is the speed lower? Well, this tells you why. I'm going to compare this to this. Okay, so in this case here, I'm going to say this wave has some wavelength lambda naught in air, because that's where we typically see most of the light that is incident on our eyes. Unless, you go into water and you look around, but it's mostly air. So that if I take c and divide by n, what's going to happen is I'm going to get lambda. This lambda naught is going to divide by n in order to become lambda. Right? So it's like I'm taking this, divide by n. Where does the divide by n go over here? It turns out it goes on the wavelength. And you'd say, well, wait a sec, how do I know that? What about the frequency? Why is the frequency not changed? Well, It other without going into huge explanations about why the frequency is not changed. First of all, the frequency doesn't change. In other words, if something was vibrating at 30 times per second and it goes into water, it's still going to vibrate at 30 times per second. All right, if it's an electromagnetic wave. If it's a mechanical thing, then maybe not. But the point being here is that when it goes across a boundary, right? When electromagnetic waves cross a boundary, the frequency is preserved, and the frequency is the thing that doesn't change. But what does change is how far effectively the wave travels in the same amount of time. It gets smaller, and that's why the speed is reduced. It doesn't go as far. It goes this far, and that means the wavelength is smaller. So if I draw it like this, what's going to happen is I'm going to get a wave that starts here and goes like this and then goes like this. And I'm saying, if I say my screen is, say, right here, right, what kind of interference are we getting? Oh, it turns out we're going to be looking at almost constructive interference in this case, because they're coming out just about at the same point in their cycles, right? They're going down and then coming out like that. So what would have happened is this block reduced the wavelength, but it still emerged, right? You can see here it emerged the same exact point in its wave as the top one. So from then on, it was exactly the same. All right. So one question you might have is, okay, if we're going to compare this, well, this and this are going to be the same, right? If I look from this point forwards, nothing there has changed. If I look at this point backwards, nothing there has changed. The change happens right in here. So what we want to do is look at how many wavelengths went on in that distance there for the top wave versus the bottom wave. Because if I figure out how many wavelengths they've gone through, then I can take a difference and figure out what's the difference in their phase. Okay, so what I want to figure out here is the difference in the number of wavelengths traveled. Maybe I could call that a delta and lambda. All right, so this wave, like I said before, has the same wavelength and is coherent. Let's suppose we know what that wavelength is in air, so lambda naught, suppose we know what that is. We're going to want to know what this index is in order to figure out what the wavelength in the index is, because we need to divide. All right, so what we're going to look at, we're going to say the distance here, we're going to call that L. Okay, so how many wavelengths does it go through? Okay, so this is just like right back to the tire example, right? If I draw an arrow on the top of the tire and I go, okay, the tire is going to rotate all the way around as it goes like this. Okay, it went through 2 revolutions. Okay, that's the same as 2 circumferences, right? So, okay, how much distance how many wavelengths occur in this amount of distance? Well, in the top wave, the number of wavelengths in the distance L is just L divided by lambda naught. I'll call that N1, or I should call that N naught, I suppose. No. Right? How many wavelengths did the top wave travel in between the size of the block boundaries, right? Well, it's how far that is and how many times it goes up and down in that time. All right, so that's how many there are. Same thing happens here. I'm going to get L divided by lambda naught divided by N, right? Because this wavelength is reduced, And that's going to be the number of wavelengths that the wave traveled in the block when the wavelength was reduced. So if I want to find the difference, all I got to do is subtract those two things, right? I got to just do n1 minus n0. That's a delta in the number. And so if I just flip this up, you'll see that it becomes n minus 1 times L divided by lambda naught. Okay, now I did this in air, which gave me the ability to say that this index was 1, and that's why you're seeing a 1 pop up here. Okay, if that was a different index compared to some other index, well, then I get a difference in the indices between the two. Okay. At that point, I'd be able to say, oh, it's how many wavelengths different? Is it 1 full wavelength? Is it 2 full wavelengths? Do you see where I'm going here? Is it 3 full wavelengths? If it's 3 full wavelengths different, guess what kind of construction we're going to have? Guess what kind of construction we're going to have? No. Guess what kind of interference we're going to have? All right. Constructive. If it's a half wavelength different, guess what kind of interference we're going to have? Destructive. You see the similarities here is the same thing as with the double slit. Okay. If I get a half wavelength difference, I get destructive interference. If I get a full wavelength, I get constructive, and it just kind of goes on. Same idea here. But unfortunately, I am realizing that this is going to have to wrap it up for today. And we will pick up here again tomorrow. Don't forget, PLC 4 is out and ready. I will just double check on that to make sure, but I'm pretty sure it is. Homework 2 is up and going, and with the info from yesterday and today, you should be able to get going on some of the double slit problems and possibly also some of the wavelength reducing problems. So have some fun with those. Let me know how things are going, and I will see you right back here tomorrow. All right, happy rest of your day, folks, and I hope you can stay dry. It does look like it's threatening again. So good luck.